Okay, let's dive in. Picture this for a second. Imagine something like incredibly small. So small its whole structure could fit inside the width of one of your hairs.
Wow.
Not just, a tiny speck, but a complex shape you'd recognize. Sounds like science fiction, maybe? Or a cartoon?
Yeah, absolutely. But it's actually real. It's a real thing scientists have made.
And it really makes you rethink scale, doesn't it? And precision.
Right.
What's even possible at that, truly micro level?
It definitely pushes those boundaries.
And that mix, the sort of whimsical idea and the really advanced tech, that's exactly what we're getting into today. We're exploring nanotechnology, looking specifically at this really cool, kind of quirky creation from Loughborough University over in the UK. They're calling it the world's smallest violin.
Which is, obviously a very playful name, but it represents some seriously sophisticated science and engineering behind it.
Totally. So to really unpack this tiny wonder and what it means, we've pulled together, a good range of sources for this deep dive. We looked at science news sites like IFL Science, mainstream news like BBC News, tech sites like Tom's Hardware.
Mm-hmm.
The official news release from Loughborough University itself, so we get the researcher's angle, and even checked out some commentary on tech forums like Slashdot just to see how people are talking about it.
Right. A good mix covers the science, the reporting, and the kind of public reaction.
Exactly. So our mission here is to go beyond just the headline, beyond the, wow, that's tiny reaction. We want to understand how they actually made something so small, so precisely, and why a violin. Trace that cultural connection.
Ah, the cultural bit is interesting.
Yeah. And most importantly, what does this fun little creation really show us about the cutting-edge research happening at the nanoscale? Research that isn't just about making tiny curiosities, but could genuinely, pave the way for the next big leaps in computers, data storage, all that stuff.
It's a really clever way to use something relatable, even funny, to shine a light on some pretty complex fundamental science capabilities.
Couldn't agree more. So let's get informed. Starting with the object itself, this world's smallest violin, what is it actually made of? What are its dimensions?
Okay, so the sources are pretty clear on the basics. It's made of platinum. That's the material they actually fabricated the structure from.
Platinum? Huh. Okay, not some exotic new nanomaterial, but a metal we know. Is there a reason for that? Maybe something to do with how they made it?
Well, platinum's often used in nanofabrication. It's very stable, conducts well, and it's compatible with a lot of the deposition methods used at this scale. And for this particular process, which we'll get into, they were essentially filling a tiny mold. Platinum works really well for creating sharp, durable structures that small.
Okay, makes sense. A tiny platinum structure. And the size, again, that's the bit that's hard to grasp.
It really is. The sources say it's just 35 microns long and 13 microns wide. Now, to get a feel for that, a micron, or a micrometer, is 1/millionth of a meter.
A millionth? Okay, yeah.
Think about the period at the end of this sentence if it were printed. That's maybe, 500 microns across? This violin is way, way smaller than that.
Wow. Okay, need more context. Let's use those comparisons from the sources. How does 35 by 13 microns compare to, say, a human hair?
Right. The hair comparison is probably the best one. A human hair's diameter varies a lot, anywhere from maybe 17 microns for really fine hair up to 180 for coarse hair.
Okay.
So this violin, at 13 microns wide, it's actually thinner than almost any human hair you'd find.
Thinner than a hair.
Yeah. And its whole length, 35 microns, is only about twice the width of the very finest hairs, significantly less than most. You could literally lay it across a single strand of hair, and it probably wouldn't even reach the other side for most hairs.
Okay, that paints a picture. Thinner than a hair. What about those little microscopic critters, the tardigrades, the water bears?
Ugh, tardigrades. Everyone loves tardigrades. They're tough little guys. But even they are giants compared to this. Tardigrades usually range from about 50 microns for the smallest ones, up to over 1,000 microns or 1.2 millimeters for the big ones.
So even the tiniest tardigrade
is still noticeably bigger than this violin.
Yeah.
If a tardigrade were playing this thing, it'd look pretty comical.
Okay, a tardigrade fiddler. Got it. So platinum structure, violin shape, 35 by 13 microns, thinner than hair, smaller than a water bear. Now, it's important, like the sources say, to be clear what this actually is and what it isn't.
Absolutely crucial point. The sources emphasize this is a microscopic structure, or you could call it an image, shaped like a violin. It is not a working musical instrument.
Right. No tiny concerts happening.
No, definitely not. As one Article joked, you can't shrink yourself down and play it. It doesn't have working strings. It can't vibrate to make sound at that scale. It's basically a nanoscale sculpture.
Okay. And the claim, world's smallest? The university is a bit careful there, right?
They are. Their own press release and the articles following it tend to say they believe it might be the smallest. Maybe based on checking records, but they haven't, submitted it to Guinness World Records for official confirmation.
But everyone agrees it's incredibly small.
Oh, absolutely.
Yeah.
All sources agree it's extremely tiny
Right.
and represents a really impressive technical feat in making something that precise at that scale. No question about that.
Okay. So, super tiny, precisely made platinum violin structure. Which leads us straight to the next big question. Why? Why a violin shape? Out of all the things they could have made.
Right. And this is where it gets kind of fun and clever. The violin shape was totally intentional, very playful. It's a direct nod to that phrase everyone knows.
Yes. Can you hear the world's smallest violin playing just for you? The classic put down.
Exactly that one. And everyone knows what it means, right? It's sarcastic. You say it when someone's complaining about something trivial, being overly dramatic.
Yeah, when their suffering is supposedly so minor, it only deserves the tiniest, quietest sympathy.
Precisely. It implies their problem is insignificant. And you often do that little hand gesture, rubbing your thumb and finger together.
Miming playing the tiny violin. Yeah, that seals the deal.
It really does. And the sources actually dug into where that phrase might have come from, which is kind of interesting.
Oh, where did it start?
Well, the thinking is it really took off on TV back in the 70s. Several sources, including Classic FM, who looked into it, point to the show MAS.
MAH, okay, I can see that.
Yeah, apparently there's a specific mention noted in 1978 that really helped cement it in popular culture.
And it clearly stuck around.
Oh, definitely. It's shown up everywhere since, even in cartoons like SpongeBob SquarePants, reaching newer generations.
Mm-hmm.
The fact that a classical music station like Classic FM wrote about its origins just shows how, embedded it is in our culture.
That's wild. So the scientists knew this, obviously, and decided to literally make the thing people joke about.
Exactly. And it wasn't just for laughs, though I'm sure they enjoyed it. It actually served a really smart purpose for communicating their science.
How so?
Well, think about it. Nanotechnology, nanoscale science. It's often really abstract, hard to visualize, hard for people outside the field to connect with.
Right. It's not intuitive.
But by choosing a shape linked to this widely understood, kind of humorous cultural reference, they instantly made their work more approachable, more relatable, more interesting.
It's a hook. It connects the super technical, microscopic thing to something people already recognize and have a feeling about, even if it's just amusement.
You got it. It got headlines, made people curious, and gave them an opening to talk about the amazing technology that made it possible. It shows that, cutting-edge science doesn't have to be presented as just dry research papers. It can be creative, it can be engaging, fun even.
Yeah, much better than just saying we refined our nanolithography process. Okay, so the violin is the catchy demo piece, picked for its cultural touch. Now the big question, how on earth did they actually build this tiny thing so perfectly? This sounds like some serious tech was involved.
Oh, absolutely. This wasn't done with, standard chip-making techniques. The sources explained it was created using Loughborough University's new, very advanced nanolithography system, which is a major piece of kit.
Nanolithography system. Okay, nano for billionth, lithography for writing or etching. So super tiny writing.
That's the basic idea, yeah. It's a whole suite of technologies designed specifically to build and study things at the nanoscale. The university emphasizes this system is big. It takes up a whole lab, not just one machine. It's a serious investment in their research power.
A whole lab for making atom-scale stuff. Wow. Within that system, what was the actual tool that carved the violin?
The star player for the violin itself was a machine called the nanofraser. It's made by a Swiss company, Heidelberg Instruments, and the technique it uses is called thermal scanning probe lithography.
Thermal scanning probe lithography. Okay, break that down. Thermal heat, scanning probe like a tiny tip moving over a surface, lithography writing. So writing with a hot tip.
That's a really good way to put it, yeah. The nanofraser has this incredibly sharp, needle-like tip. Think way sharper than a needle. And it can be heated up really hot.
Okay.
This tip is part of what's called an atomic force microscope, or AFM, which means it can scan a surface with insane precision, basically feeling the atoms. But for lithography, instead of just feeling, the heated tip is used to directly change a special material coated onto the chip.
So it's like not quite a 3D printer adding material, but maybe like an atomic scale wood burner using heat to carve or change the surface?
Yeah, more like an engraver or etcher using heat,
Right.
exactly. As this super hot tip traces the pattern, the violin shape, it basically burns away or vaporizes the material it touches on the surface, but in a very, very controlled way. This allows for incredible precision. The sources say the system can get down to resolutions of 15 nanometers.
15 nanometers. Okay, a nanometer is a billionth of a meter. So the tool can make features roughly 1,000 times smaller than a micron, even smaller than the violin itself, which is measured in tens of microns.
Exactly. The tool's resolution is much finer than the violin features, which just shows you what it's capable of for potentially even more detailed work. Professor Morrison, who heads physics there, described the tip's sensitivity nicely. She called it a very, very, very small needle that can see atomic interaction.
See, atomic interaction. Wow, that drives home the scale. Okay, so they have this nanofraser, this incredibly sharp, hot tip. How did they use it and the rest of the system to go from a blank chip to a platinum violin? Can you walk us through the steps?
Sure thing. So first you start with a small piece of silicon, like a tiny chip. That's your base, your substrate. And you coat this chip with 2 layers of a special material called a resist.
Resist.
Yeah, it's usually some kind of polymer, kind of like a gel. It's designed to be sensitive to that heat from the nanofraser tip. Think of it like the canvas or the wax tablet the hot stylus will write on.
Okay, chip coated with 2 layers of this heat-sensitive resist. Step 1.
Right. Step 2. Put the coated chip into the nanofraser machine. The heated tip then starts scanning across the top layer of the resist, tracing out the violin pattern precisely. Wherever the hot tip touches, it changes the resist, usually by vaporizing it, literally burning it away, or maybe changing its chemistry.
So the heat creates the violin outline by removing or altering the top resist layer.
Exactly. Step 3 is called developing. After the pattern is written, you wash the chip with specific chemicals, solvents usually. These chemicals selectively dissolve away only the parts of the resist that were hit by the hot tip.
Ah, okay.
So the developer washes away the resist where the violin pattern was drawn, leaving behind a tiny violin-shaped trench or cavity in the resist layer, exposing the layer underneath.
Okay, so now you've got a tiny sunken mold, basically, in the shape of a violin etched into the resist. What's next?
Step 4. Deposit the platinum. The chip, with its violin-shaped cavity, gets moved to another part of the system, and then a thin layer of platinum is coated over the entire chip surface. This might be done using techniques like sputtering or evaporation, basically raining platinum atoms down. And crucially, the platinum fills up that tiny violin-shaped cavity.
So it fills in the mold.
Exactly. It perfectly takes the shape of that cavity. Then the final step, step 5, is called liftoff. You dunk the whole chip in another solvent, like acetone. This solvent is chosen because it dissolves the remaining resist material, the stuff that wasn't hit by the hot tip and wasn't washed away earlier.
Right.
And because the platinum layer was sitting on top of that remaining resist, when the resist dissolves, it lifts away all the unwanted platinum that was just sitting on the surface. The only platinum left behind is the stuff that settled down into the violin-shaped cavity on the chip itself.
Leaving just the platinum violin, that's surprisingly elegant,
Yeah.
using the resist like a temporary stencil or scaffold. And doing all this sounds like it needs an incredibly clean space.
Oh, absolutely. You can't do this on an open lab bench. The whole nanolithography system is inside a completely enclosed setup. Uses things like glove boxes, interconnected sealed chambers.
Why it's so sealed off?
Contamination is the absolute killer at this scale. A single speck of dust, a tiny water molecule from someone's breath, even oils from skin. They're gigantic compared to these nanoscale features. They could completely wreck the process or the final structure. So the enclosed system keeps everything ultra clean, ultra dry, often under vacuum, or filled with an inert gas like nitrogen or argon.
So researchers are working through gloves, manipulating things inside this super clean box. How do they even move the chip between, say, the nanofraser stage and the platinum deposition stage?
Yeah, the sources mention they have automated mechanisms inside, described as small metal arms. These carefully transfer the chips between the different chambers without ever exposing them to the outside air. It's all about maintaining that pristine, controlled environment from start to finish.
Like a tiny high-tech assembly line inside a bubble. Amazing.
Once they got the process down, how long did it take to actually make one violin?
Once everything was calibrated and optimized, making one violin structure takes about 3 hours, apparently. Which is pretty quick, relatively speaking.
3 hours. Okay.
But, and this is important, The sources are very clear that getting to that point, perfecting the recipe, basically, to reliably make the final version that took the research team several months of hard work.
Months of R&D for one tiny violin, that really highlights that this wasn't just hitting print.
Not at all. Those months were all about figuring things out, tweaking the tip temperature, the standing speed, how thick the resist layers should be, the right developer chemicals, the platinum deposition settings, all that stuff. It was the fundamental research and engineering needed to learn how to control the process to make this specific thing reliably with their new equipment. The 3 hours is just the runtime once you know exactly what to do. The months were the discovery part. That makes total sense.
Yep.
It was about mastering the method, not just making the object. And that really brings us back to the university's main point, right? The violin, however cool, wasn't the end goal. It was, like Professor Morrison said, a demonstration of what this new system can do.
Exactly. Its main job was to be a really clear, really memorable test case. Something to show off unequivocally the amazing precision manufacturing capabilities of their new nanolithography setup, especially that nanofraser tool.
It's like if you get a fancy new set of woodworking tools, you might build an intricate, beautiful birdhouse first, just to show everyone and yourself what the tools are capable of in skilled hands.
That's a great analogy. Professor Morrison emphasized the level of control and possibilities we have with the setup.
The violin, because it's recognizable but also has fine details, and its size is relatable through those hair and tardigrade comparisons, it just made that control and precision visible and compelling. To other scientists, sure, but also to the public. And the sources stress this isn't just about showing off. This demonstration, this mastery of the technique, it's the foundation for much bigger things.
Absolutely critical point. Professor Morrison explicitly said, a lot of what we've learned in the process has actually laid the groundwork for the research we're now undertaking. Perfecting the violin taught them how to operate the system with the finesse needed for their real research goals. This isn't a toy-making machine. It's a serious scientific instrument they learned to use by making the violin.
So what is that real research now? What are the big science questions they're tackling with this capability?
Well, the system lets them build these precisely designed nanoscale structures out of specific materials. And once they've built them, they can then poke and prod them, basically. They can shine light on them, apply magnetic fields, pass electric currents through them, and see how the materials and structures respond at that tiny scale.
Okay.
Understanding how materials behave differently when they're nano-sized compared to when they're in bulk, that's fundamental science. Properties can change dramatically down there.
Right, so they prove they can build tiny, precise things. Now they're using that skill to make miniature experiments to study material physics at the nanoscale.
That's exactly it. And knowing that basic science is what lets you develop new technologies, these specific projects the sources highlight are really exciting. They're focused on finding new materials and new ways to build the next generation of computing devices, things that could push past the limits of current tech, and also looking into new ways to harvest energy.
Future computing and energy. Yeah, those are definitely big deals. Let's look at the first project mentioned, Dr. Naomi Leo's work. It's about harnessing heat.
Yes, and this is super relevant because heat is a massive issue in basically all modern electronics. Computers, phones, data centers, they use a ton of electricity. And a lot of that just gets wasted as heat.
Right, inefficiency plus things overheating.
Exactly. Too much heat slows things down, limits how small you can make stuff, and can even fry components. So heat is mostly seen as a problem you need to get rid of.
Okay. But her research sees it differently.
Kind of, yeah. She's exploring whether heat, specifically differences in heat temperature gradients where one spot is hotter than another nearby spot, can actually be used to create useful effects within materials at the nanoscale.
Useful effects from a temperature difference. How does that work?
Well, down at the nanoscale, in certain materials, heat flow can be linked to other things, like generating electrical currents or changing magnetic states. This is the basis of things like thermoelectric generators, where heat difference makes electricity. Dr. Leo's research is looking at how to precisely create and control these tiny temperature gradients to potentially drive new ways of storing data or performing calculations, possibly faster, and using less energy than current methods.
So instead of just using electrons moving around, she's trying to use heat flow or effects driven by heat flow to manipulate information.
That's the core idea. And her approach involves combining different kinds of materials, magnetic ones, electric ones, together with custom-designed nanoparticles. These nanoparticles are engineered to absorb specific colors, specific wavelengths of light. When you shine that specific light on them, they absorb it and turn it into heat right there, very locally. So, by shining patterns of light, She can basically paint hotspots and create these precise temperature gradients exactly where she wants them within the device structure.
So using light and special nanoparticles to create controlled hot and cold zones, and then seeing if those heat patterns can do useful computing work.
That's a good way to think about it. And this is where that nanolithography system, the one that made the violin, is absolutely essential.
Ah, right, because building that device.
Exactly. To make these ideas work, she has to integrate all these different components, the magnetic layers, the electric contacts, the heat-generating nanoparticles onto one tiny chip, often patterned side by side or stacked very precisely. That requires manufacturing with extreme nanoscale accuracy, making sure everything lines up perfectly so the heat gradients interact correctly with the magnetic and electric parts. The nanofraser's ability to do that kind of precise, multi-material sort of 2.5D patterning is vital for building the complex prototypes she needs for her experiments.
It's not just making one tiny thing, it's assembling a tiny intricate system with multiple interacting parts.
Got it. And her being a Eukaryote Future Leaders Fellow, that suggests this research is seen as having real potential.
It definitely signals that it's considered a promising, high-impact direction. Now, the second major project they highlighted is led by Dr. Faisal Dajeen, and this one's focused on new materials for magnetic data storage.
Magnetic storage. So like hard drives, or MRAM, maybe.
Pretty much. Traditional hard drives, as you know, store data by flipping the magnetic direction of tiny regions on a disk. A read head detects those magnetic changes. How small you can make those magnetic bits and how sensitively you can read them determines your data density, how much info fits in a space.
And we always want more density, store more in less space.
Always. But there's a fundamental problem. As you try to make those magnetic bits smaller and smaller for density and also for energy efficiency, you hit a wall because of physics. At really tiny sizes, the magnetic direction of these bits can become unstable just due to the normal heat energy bouncing around at room temperature. Right, they just randomly flip.
Exactly. It's called superparamagnetism. The thermal energy is enough to overcome the magnetic stability, and the bit loses its stored 0 or 1. Poof, data corrupted. This puts a hard limit on how small you can make bits using current materials.
Superparamagnetism. Okay, so you need either much better sensors or fundamentally different materials.
Precisely. You either need incredibly sensitive reheads that can reliably detect the state of very small, maybe weaker bits, or you need new materials that are just inherently more magnetically stable even when they're shrunk down to those nanoscale dimensions.
And Dr. Dajeen is working on the materials side?
That's right. He's investigating whether some newly discovered or engineered materials, often called quantum materials, could be the answer. These are materials where quantum mechanics plays a really dominant role in how their electrons behave and interact, especially regarding magnetism. This can give them unique properties you don't see in ordinary materials.
Quantum materials? How could they be better for storage?
Well, the hope is that some of these materials might naturally hold on to their magnetic state more strongly, even at very small sizes, fighting off that thermal flipping, that superparamagnetism. Or they might interact with electric currents or magnetic fields in new ways that allow for faster data writing or more efficient reading. He's exploring these quantum effects to see if they can lead to magnetic memory that's denser, faster, and more reliable.
So looking for materials where the fundamental physics works differently at that tiny scale to get around the limitations of current stuff.
Exactly. And it's not just about better hard drives. The sources also mentioned potential applications in things like brain-inspired computing.
Neuromorphic computing.
Yeah, those kinds of architectures that try to mimic how biological brains process information. They often need new types of memory and processing elements that work differently than traditional silicon chips. Dr. Dajeen's work on stable nanoscale magnets could be really important for developing those kinds of future systems, too.
Wow, okay. That's definitely pushing towards new computing paradigms. And again, the nanolithography system is key for him, too.
Absolutely. He needs to be able to actually build tiny test structures using these new quantum materials. He needs to fabricate nanoscale prototypes of potential memory bits or sensor elements with extreme precision. The nanofraser allows him to pattern these specific, often exotic materials accurately, integrate them into test devices, and then actually measure their properties, their magnetic stability, how they respond to fields, and compare them directly to existing technologies.
So Same story as with the heat research.
Uh,
The system that made the violin is now the essential tool for building the miniature experiments and prototypes needed to test these really advanced ideas about future computer materials.
That's the absolute crux of it.
Right.
The violin was the eye-catching proof of concept for the tool, and now that tool is enabling researchers like Dr. Leo and Dr. DeJean to do the fundamental science and engineering needed to build the next generation of technology. And Professor Morrison's excitement, which comes through in the sources, really reflects that. It's about the potential the system unlocks for lots of different research, not just their own group.
It paints a much bigger, much more significant picture than just, a novelty violin. It's about the tool and the critical research that tool makes possible. But hang on, we should probably also touch on some of the reactions, right? Like from those tech forums, Slashdot and others. Not everyone was immediately hailing it as revolutionary. Some people were a bit more grounded, skeptical, maybe.
Yeah, that's a fair point and important context. When the news broke, you definitely saw comments pointing out things we've already mentioned, like, okay, it's a picture, it's a structure, it doesn't play music, which is true.
Right.
Others compared it to things that are even smaller, like IBM's A Boy and His Atom movie back in 2013. Remember that? They used an AFM tip to literally push individual atoms around to make frames for stop-motion animation. That's working at the angstrom or single nanometer scale, which is orders of magnitude smaller than the tens of microns in the violin.
Good point. Atomic scale versus micron scale, big difference. And others said, well, look at microchips. They have incredibly complex patterns etched with resolutions much finer than this violin.
Also true, modern semiconductor manufacturing involves lithography with feature sizes down in the single-digit nanometers, far smaller than the overall violin structure, and vastly more complex in terms of density. So those points are technically valid, often coming from people who know about existing capabilities in different areas of nano and microfabrication.
Okay, so given those valid points, it's not functional. Atom manipulation is smaller, chip etching is denser. How do we place the significance of the Loughborough violin? Why was it still presented as this important demonstration?
It really comes back to understanding what specific capability it was demonstrating. It wasn't trying to be the absolute smallest thing ever made, or the most complex pattern. Its significance is tied directly to the capabilities of the nanofraser tool and that specific nanolithography system for doing a certain type of fabrication relevant to their research goals.
Ah, okay. So it's about the specific technique and its application.
Exactly. The nanofraser uses thermal scanning probe lithography. This technique is really good for creating high-resolution patterns, often with some depth, that 2.5D aspect, and crucially, it's very versatile. It can work with a wide range of different materials beyond just silicon and photoresists used in chip making. And it excels at integrating these different materials together precisely on one device.
Which is exactly what those research projects needed, right? Combining magnetic, electric, optical materials.
Precisely. While chip lithography is amazing for mass-producing silicon circuits, the nanofraser offers a different kind of flexibility and precision that's ideal for research and prototyping with novel materials at the scales tens of nanometers up to microns, where the interesting physics for next-gen computing and sensors often happens. The violins show they can master that specific tool to make complex shapes reliably.
Okay, so the violin was a smart, easy-to-understand published showcase of the system's ability to do the exact kind of precise, multi-material fabrication needed for the actual cutting-edge research happening in that lab. It made an abstract capability tangible.
You nailed it. It used that cultural hook to highlight a specific technical achievement that's now enabling research aimed squarely at overcoming fundamental roadblocks in current computing technology.
And that ties into the bigger picture, doesn't it? This constant push in technology for smaller, faster, more efficient, especially as things like Moore's Law seem to be slowing down for traditional silicon chips. This kind of research isn't just tweaking the old ways, it's exploring fundamentally new ways to compute and store information.
It's exactly that. It's fundamental physics meets advanced engineering, using sophisticated tools to lay the groundwork for whatever comes next after our current technologies hit their physical limits. The violin was just the charming, microscopic ambassador for all that serious work.
Okay, this has been a fantastic deep dive. We've gone from a, let's say, charmingly tiny object to the real frontiers of computing research. Let's just quickly recap the key things for everyone listening. We started with this image, the world's smallest violin, platinum structure, just 35 by 13 microns, thinner than a hair, smaller than a tardigrade.
We clarified it's a microscopic structure, not a playable instrument. And its shape was a deliberate, playful nod to that famous pop culture phrase, A really clever bit of science communication to get attention.
Then we dug into the how. Made using Loughborough University's advanced nanolithography system, especially the nano-Fraser tool using thermal scanning probe lithography. That hot, sharp-tip writing patterns in a resist layer, followed by platinum deposition and liftoff, all inside an ultra-clean, controlled environment. And remembering it took months of work to perfect that process.
And we stressed that the violin, while impressive, was mainly a demonstration of the system's capability. That powerful system is now the engine driving really high-impact research. We talked about Dr. Naomi Leo's work using precise light-induced heat gradients in combined materials for potential energy-efficient computing.
Right, harnessing heat itself. And Dr. Fazil Dejane's research exploring new quantum materials, using the system to build prototypes to see if these materials can overcome the stability limits of current magnetic data storage, aiming for denser, faster memory, maybe even for brain-inspired computing.
And we contextualized it, acknowledging the comparisons to atom manipulation or chip etching, but reframing the violin as showcasing the nano-Fraser system's specific strengths in precise, flexible, multi-material fabrication, exactly what's needed for this kind of exploratory research into future technologies beyond current limits.
It really shows how science often uses these sometimes surprising benchmarks or demos to prove a capability that then opens up whole new fields of inquiry.
Exactly.
So why does this matter to you, listening right now, whether you're deep in tech or just curious about where things are going?
Well, because this kind of fundamental research, the stuff demonstrated by a quirky little violin, is directly shaping the future of the technology you use every day. It's about pushing physics and engineering to their limits to make computers potentially faster, store way more data, use less energy, maybe even work in completely new ways we haven't fully imagined yet. It's science and, frankly, creativity working together, showing that even the most complex science has roots in understanding how stuff works at the very smallest scales. And that connects directly to the devices that define our world.
Absolutely. Which leaves us with, I think, a really interesting final thought to chew on. If we can now engineer materials and build structures smaller than dust specks with enough precision to start controlling things like heat flow and magnetism for computing, what other fundamental forces or properties of nature might become accessible at the nanoscale as these tools get even better? What currently unimaginable technologies might we unlock when we can truly engineer matter atom by atom, molecule by molecule, with this kind of deliberate control?